Hello, and welcome back. My name is Liam, and this is Deep Space Intelligence, the channel where we take the most compelling stories happening at the intersection of science, Earth, and the cosmos, and we bring them to you with the depth and care they deserve. Whether we're tracking the pulse of distant stars or listening to the trembling of the ground beneath our feet, this is a place for serious curiosity. And today, the ground itself has a story to tell. Somewhere in the high desert of central Nevada, in a stretch of empty land where the horizon stretches so flat and wide it looks like the edge of the world, the Earth has been shaking, not once, not a dozen times, hundreds of times, over the course of weeks, in a relentless rolling sequence that scientists are still working to fully understand. And the detail that elevates this from a routine geological report to something genuinely remarkable is this. The fault responsible for all of it, the fracture buried deep in the ancient rock that has been releasing all this energy, was completely unknown. Nobody had mapped it. Nobody had named it. It was not in any database, not on any hazard chart, not in any model used to plan roads or buildings or emergency responses in the surrounding region. It lay there in the dark beneath the Nevada desert for thousands of years, and the only way science finally learned it existed was because it broke open and started shaking. That is the story we're exploring today. It is a story about a living, restless planet that still holds secrets even from the most sophisticated monitoring systems humanity has ever built. It is a story about the invisible architecture beneath the American West, about the forces that have been quietly tearing the land apart for tens of millions of years, and about what it means when the Earth reveals a piece of itself that no one knew was there. Let us begin at the beginning, with the place itself. Nevada is not a state most people associate with earthquakes. If you ask someone in the street which American states shake the most, they will almost certainly say California. Some might add Alaska. A few would know that the Pacific Northwest carries serious risk. But Nevada, with its casino-lit boulevards and sun-bleached desert ranges, rarely enters the conversation. That perception is badly mistaken. Nevada is the third most seismically active state in the entire United States, trailing only California and Alaska, and it has held that ranking for as long as systematic records have been kept. The National Park Service has long noted that faults are located around nearly every significant mountain range in the state. A magnitude 6.0 or greater earthquake occurs in Nevada roughly once every 10 years. Earthquakes of magnitude 7.0 or higher strike the state approximately once every 3 decades. The largest earthquake ever recorded in Nevada measured a magnitude 7.3 and occurred on October 2, 1915, near Pleasant Valley in the central part of the state. That single event remains one of the most powerful continental earthquakes in American history, and it left surface ruptures that geologists can still trace today, more than a century later. So Nevada shakes. It has always shaken. The question worth asking is not whether the state is seismically active, because the answer to that has never been in doubt. The question is why. To understand that, you need to understand the landscape itself at a scale that no map quite captures. Look at Nevada from above, from a satellite image or a topographic chart, and you will notice something unusual about its terrain. The state is covered in long, parallel mountain ranges separated by flat, narrow valleys. Range after range, valley after valley, stretching in roughly north-south corridors across the entire state. This is not a coincidence of erosion or an accident of drainage. It is the surface expression of something profound happening deep in the crust below, a process that has been underway for approximately 40 million years and shows no signs of stopping. What you're looking at is the Basin and Range Province, one of the most geologically distinctive regions on the surface of the Earth. The crust beneath the basin and range is being stretched, pulled apart in a broadly east-west direction by forces that operate at the scale of tectonic plates. As this stretching occurs, the crust fractures along what geologists call normal faults, which are cracks in the rock where one side drops down relative to the other. When one block drops, it forms a valley, which geologists call a graben. When a block stays elevated between two dropping zones, it forms a mountain range, called a horst. That alternating pattern of dropped basins and elevated ranges is exactly what you see when you look at Nevada from space. The landscape is literally the surface scar of millions of years of crustal rupture. The average crustal thickness across the Basin and Range Province is roughly 30 to 35 kilometers, which is actually quite thin compared to unextended continental crust. That thinning is the product of all this stretching. The region has expanded by amounts that vary considerably from place to place, with some areas having stretched by as much as 100% of their original width, meaning the crust there is now roughly twice as wide as it was before extension began. Beneath the thinner crust, the heat of the mantle sits closer to the surface, which is why Nevada and surrounding states have such a high density of geothermal features, hot springs and volcanic remnants. This ongoing stretching is not hypothetical or historical. It is happening right now. Geodetic surveys using networks of GPS instruments have measured the ground surface slowly moving, millimetre by millimetre, year after year. Instruments can detect the almost imperceptible creep of the landscape as the plates pull apart. That motion accumulates on faults, and when the stress on any given fault reaches the breaking point, the rocks slip and the ground shakes. Running along the western edge of this stretching province, roughly parallel to the border between Nevada and California, is a zone of especially concentrated deformation called the walkerlane. The walkerlane is not a single fault. It is a broad corridor of faults, several of them major, that collectively accommodate somewhere between 15 and 25% of the total relative motion between the Pacific Plate and the North American Plate. The rest of that motion, the remaining 75% or more, happens along the famous San Andreas Fault system in California. But the walkerlane is not a minor player. It handles a substantial portion of the largest ongoing tectonic interaction in the continental United States. What makes the walkerlane particularly interesting to geologists and seismologists is that it may be in the early stages of a much larger transformation. Some researchers at the University of Nevada, Reno, have described it as being in a state comparable to where the San Andreas Fault system was 20 to 30 million years ago, in its developmental infancy but building towards something significant. The walkerlane may, over a geological timescale of several million years, eventually become the dominant plate boundary on the west coast of North America, potentially supplanting the San Andreas entirely. If that process continues, the city of Reno would eventually sit near a coastline. The numbers involved are staggering in their timescale, but the direction of travel is there in the data. The walkerlane generates serious earthquakes. In 1932, the magnitude 7.2 Cedar Mountain earthquake struck along its western margin. In 1954, a remarkable series of large earthquakes struck Nevada in a short period, including the magnitude 7.2 Fairview Peak earthquake and the magnitude 6.9 Dixie Valley earthquake, both on the same day, December 16, 1954. These events left surface ruptures stretching for dozens of kilometers across the desert. In 2020, the magnitude 6.5 Monte Cristo Range earthquake struck Nevada, the largest earthquake in the state since those 1954 events, and by some measures the largest walkerlane earthquake since 2019's Ridgecrest sequence just across the border in California. Parallel to and intersecting with the walkerlane is a zone seismologists call the Central Nevada Seismic Belt. This is a semi-continuous corridor extending for more than 300 kilometers through central Nevada, and it has hosted some of the largest earthquakes in the western United States outside of California. The 1915 Pleasant Valley earthquake, the 1932 Cedar Mountain event, and the sequence of 1954 ruptures all fall within or adjacent to this belt. The Central Nevada Seismic Belt represents a zone where the combined stresses of walkerlane shear and basin and range extension interact, creating a region where major earthquakes are not merely possible, but essentially inevitable over geological time. Within this context of widespread, ongoing tectonic activity, earthquake swarms are not unusual in Nevada. A swarm, in seismological terms, is a sequence of earthquakes where there is no single, clear main shock followed by progressively smaller aftershocks. Instead, swarms involve many earthquakes of roughly similar magnitude, clustered in time and space, without any one event clearly dominating. Swarms can last hours, days, weeks, or sometimes months. They occur frequently across Nevada and are generally understood to reflect slow stress transfer along interconnected fault systems, sometimes combined with fluid migration through fractured rock at depth. The Nevada Seismological Laboratory, housed at the University of Nevada, Reno, monitors seismic activity across the state using a network of instruments that detect ground motion and transmit data in real time. The laboratory has catalogued thousands of events annually for decades, building a detailed picture of which fault zones are active and where stress is accumulating. That monitoring network is sophisticated by any standard, and yet what began in the late winter of 2026 managed to surprise even the scientists watching the screens. The first tremors in what would become a persistent and scientifically significant sequence began stirring in late February 2026. They centered on an area of central Nevada, roughly 75 to 90 kilometers northeast of Tonopah, a small town of about 2,000 residents in Nye County that sits at the junction of two major Nevada highways deep in the desert interior. Tonopah is the kind of place where the nearest city feels genuinely far away, where the landscape at night is so dark that the stars seem to press down toward the earth, and where the ground, most of the time, simply sits still. What the USGS instruments began recording in those final days of February was not dramatic at first. Small earthquakes, many of them below magnitude 2.0, flickered across the sensor network like distant static. These are the kinds of events that happen in Nevada constantly and rarely prompt any public notice, but they kept coming. The cluster of events began to tighten spatially, concentrated along what appeared to be a linear zone beneath the southern edges of the Monitor Range and the Antelope Range, two of those long parallel ridgelines that typify the basin and range landscape of central Nevada. Through the first days of March, the swarm intensified. By the time March 4th arrived, the Nevada Seismological Laboratory and the United States Geological Survey had catalogued nearly 100 separate events in the sequence. The vast majority of them fell between magnitudes 1.5 and 3.0, too small to cause damage but plenty large enough to be felt by anyone standing close to the epicenters. Several events climbed above magnitude 3.5, and the largest event in the early phase of the swarm, a magnitude 4.3, struck at approximately 1637 Coordinated Universal Time on March 1st, at a depth of about 11 kilometers beneath the desert surface. That magnitude 4.3 earthquake was felt far beyond Nye County. Reports flooded into the USGS Did You Feel It system from residents in Las Vegas, more than 200 miles to the south. Carson City, more than 180 miles to the northwest, also registered the shaking. A single earthquake reaching people across that kind of distance reflects just how efficiently seismic energy propagates through the relatively cool, rigid crust of the basin and range when a fault releases stress at depth. Christy Rowe, the director of the Nevada Seismological Laboratory, went on record to explain what her team was seeing. Rowe is a specialist in earthquake geology, with a doctorate from the University of California, Santa Cruz, and a distinguished career that included professorships at the University of Cape Town and McGill University, before she joined the Nevada Seismological Laboratory in 2024. Her expertise centers on the rock record of earthquakes, specifically on what happens to fault materials at the moment of rupture and in the long aftermath. She is, in other words, someone who reads earthquakes not just as data on a seismogram, but as physical events that leave their marks in stone. Rowe described the activity near Tonopah as consistent with Nevada's well-established pattern of clustered seismic events. "This is a very Nevada-style earthquake sequence," she said publicly. "We have these a lot where we just see an uptick in activity in a certain spot." That framing was accurate and measured. Swarms of this character are documented repeatedly in the geological record of the region, and the scientific community's baseline expectation for central Nevada is that clusters of shallow normal faulting events will appear periodically, run for a period of days to weeks, and then subside as the local stress field readjusts. But what stood out in this case, the detail that elevated the Tonopah swarm from a routine entry in the earthquake catalogue to something scientifically compelling, was the specific fault involved. When Rowe and her colleagues at the Nevada Seismological Laboratory analysed the pattern of the earthquakes, plotting their locations and depths in 3 dimensions, they found that the events were aligned along a fault stretching beneath the southern edge of the Monitor and Antelope Ranges, and that fault, when they went to cross-reference it against every geological database, every hazard map, every fault survey the state of Nevada had ever compiled, simply was not there. Rowe said it plainly and without dramatization. "We didn't know this fault was there. It's a new fault to us, not to the Earth, obviously, but it was previously unknown." That distinction she drew, new to us but not to the Earth, is worth holding on to. The fault has existed for an unknown but certainly very long period of time. It formed the way all faults form in the basin and range, through the slow accumulation of crustal stress, until the rock finally gives way and fractures. It has likely ruptured before, perhaps many times over the geological past, but it had been silent for long enough, thousands of years at least, that the surface traces of its previous activity had been worn away, buried under sediment, or eroded by the slow work of wind and water. It disappeared from the landscape, and therefore from the knowledge of the scientists who study it. This is a reality about fault mapping that deserves careful attention, because it has direct implications for how we understand seismic risk not just in Nevada, but across the entire active western United States. Nevada contains thousands of faults. Some estimates suggest the number of individual fault structures in the state runs into the tens of thousands when you include every mapped segment and subsegment. But the operative word in that sentence is mapped. Fault mapping is a painstaking, discipline-intensive process that relies on field surveys, aerial photography, satellite imagery, LiDAR scanning, and historical records of surface rupture. A fault that ruptured the surface in recent geological time, say within the last 10,000 to 20,000 years, leaves a visible scar. That scar might be a fault scarp, an abrupt step in the topography, where one side of the fault dropped relative to the other. It might be a deflected stream, where a watercourse was offset by horizontal movement along the fault. It might be a linear trough, or a long straight valley carved preferentially by erosion, along the weakened rock of the fault zone. But all of these features require time to form and maintain themselves against the constant erosion that acts on arid desert landscapes. When a fault has not ruptured for thousands of years, the scarp softens and rounds. Alluvial fans, sheets of sediment deposited by rare desert floods, bury the linear features. Vegetation colonizes the disturbed ground and further obscures it. Wind-blown sediment fills the small trenches and offsets. Given enough time, the geological fingerprint of a fault's last rupture can vanish entirely from the surface, leaving behind nothing that a field geologist or a satellite analyst would flag as suspicious. The fault lies below, intact, capable, accumulating stress toward its next rupture, but invisible to the science that is supposed to document it. Rowe articulated this process directly when explaining the discovery near Tonopah. When a fault lies quiet for thousands of years, she said, erosion can erase it from the landscape. It lies hidden until the next earthquake. That sentence captures something both scientifically important and quietly unsettling. The earthquake itself, the very event that causes concern, is also the mechanism by which knowledge is created. We learn about the fault because it breaks. Before it breaks, we have no reliable way of knowing it is there. This is not a small problem. It means that every seismic hazard map, every building code calibrated to local fault distances, every emergency management plan built on the assumption that the known faults represent the complete inventory of seismic risk, is working with an incomplete dataset. The missing faults are not scattered randomly. They are preferentially located in the same tectonic environments as the known faults, in the same basin and range extensional province, in the same walkerlane shear belt, in the same central Nevada seismic belt. The regions where we know earthquake risk is high are also the regions where hidden faults are most likely to exist. The swarm near Tonopah drew comparisons to other Nevada sequences that had demonstrated similar patterns in recent years. The Monte Cristo Range earthquake sequence of 2020 had unfolded on fault geometry that was not fully mapped in advance, and the detailed picture of the rupture had to be assembled from the aftershock pattern after the fact. The Hawthorne Swarm of 2011, another cluster of central Nevada events, similarly activated portions of the fault network that were not well characterized in the pre-existing hazard literature. Nevada, in this sense, is a state that regularly teaches seismologists things they did not know. Now, to be clear about something important at this point in our story, the scientific framing of the Tonopah sequence was calm and appropriately measured. Christy Rowe and her colleagues were not alarmed. The earthquakes remained moderate throughout, and as of early March 2026, none had exceeded magnitude 4.3. In a region as sparsely populated as the area northeast of Tonopah, even a significantly larger earthquake would be unlikely to cause serious casualties or major structural damage, simply because there are very few structures anywhere near the epicenters. Rowe indicated that the laboratory would not deploy additional temporary monitoring equipment unless activity escalated to around magnitude 5.0 or greater. That measured response reflects the professional calibration that serious seismologists bring to their work. They are not dismissive of the sequence. but they are not catastrophizing it either. What the scientific community was genuinely interested in was the opportunity the swarm presented. When an unknown fault makes itself known through seismic activity, the seismogram record becomes a kind of involuntary map. Every earthquake produces a tiny distinct signal that, when analyzed alongside hundreds of other signals from the same sequence, reveals the geometry of the fault plane, its orientation, its dip angle, its depth extent. The swarm near Tonopah was, in this sense, the desert floor broadcasting its own autobiography in seismic waves, and the instruments of the Nevada Seismological Laboratory were listening to every word. The USGS Did You Feel It system was also receiving reports. This crowdsourced tool, which allows any member of the public who experiences shaking to submit a report describing what they felt and where, serves a genuinely scientific purpose. It helps seismologists fill in the gaps between monitoring stations, giving a ground truth map of how shaking intensity varied across the region. Even reports of very light shaking from far-off communities contribute useful data. Rowe and her colleagues encouraged anyone who felt the tremors to submit a report, noting that even small contributions from the public help build the larger picture of a sequence's extent and reach. But while the scientists were carefully analyzing waveforms and cataloguing aftershocks, something else was happening in the broader information environment. The Tonopah sequence, particularly when the stronger events began registering, felt shaking across hundreds of miles of Nevada attracted public attention. And when people started looking up where exactly Tonopah was, some of them noticed something. The earthquake swarm was centered approximately 50 miles from the Tonopah test range, a deeply secretive military installation that had been conducting tests involving nuclear weapons components since 1957. This facility, sometimes called Area 52 by those who track the network of classified bases in the Nevada desert, sits within the same vast defense complex that encompasses the more famous Area 51 and the Nevada test site, where the United States detonated more than 900 nuclear weapons between 1951 and 1992. This geographical coincidence, combined with the geopolitical tension of the moment, produced a significant wave of speculation on social media. In late February and early March of 2026, with active military operations underway in the Middle East, following the killing of Supreme Leader Ayatollah Ali Khamenei in US and Israeli airstrikes, the idea of underground nuclear testing appearing to some as a plausible explanation for the desert shaking attracted attention on social media platforms and in online forums. The scientific community addressed this speculation directly and without equivocation. Both the USGS and independent academic seismologists stated clearly that the seismic waveforms, depths, and geographic pattern of the Tonopah swarm were entirely consistent with natural fault movement and entirely inconsistent with the signatures of an underground explosion. Modern seismological instruments can distinguish between the wave patterns produced by a tectonic earthquake and those produced by a detonation with considerable reliability. Explosions produce characteristic waveform signatures that differ fundamentally from the complex extended waveforms generated by fault rupture over a surface of many square kilometers. None of the seismic signals recorded in the Tonopah sequence contained any of those explosive signatures. The geology of the central Nevada seismic zone, as Rowe and her colleagues explained, fully accounts for swarms of this character without requiring any human contribution. Tonopah's history as a location associated with classified military activity and nuclear testing makes the speculation understandable in an emotional sense, even if it is groundless in a scientific one. The Nevada desert carries real history. Those 900-plus nuclear detonations at the Nevada test site were real events that produced real seismic signals felt across the region. The legacy of that testing program is embedded in the landscape in the form of subsidence craters and residual contamination that will persist for geological ages. That history gives the desert a certain resonance when the ground shakes, a residual anxiety that does not simply evaporate because the science is clear. Understanding that emotional context does not mean endorsing the speculation, but it does help explain why it arose. For those of you who like to follow these stories closely, it is worth knowing where to look for reliable information. The USGS Earthquake Hazards Program maintains a constantly updated catalogue of seismic events, and the Nevada Seismological Laboratory at the University of Nevada, Reno, publishes real-time data alongside official statements when significant sequences occur. We always encourage you to consult these primary sources directly, to look at the raw data yourselves, and to form your own informed view rather than relying on any single interpretation, including ours. Science is a process, not an answer, and the most honest thing we can do is point you toward the people doing that work. As March progressed, the Tonopah swarm began to settle into a lower-level background hum of smaller events, still logging dozens of earthquakes but with decreasing peak magnitudes. It looked, for a period, as if the sequence might be winding toward a quiet conclusion, as many Nevada swarms eventually do. The new fault in the Monitor and Antelope ranges had introduced itself, scientists had begun cataloguing its geometry, and the desert had settled into something approaching calm. But Nevada was not finished. In mid-April 2026, a different part of the state suddenly became the focus of intense seismic attention. This time, the location was not the remote interior desert around Tonopah, but a zone much closer to populated areas, near the communities of Silver Springs, Fallon and Fernley in western Nevada's Churchill and Lyon counties. This is a part of Nevada with a dramatically different character from the empty expanses around Tonopah. Silver Springs sits roughly 30 miles southeast of Carson City, the state capital. Fallon, a small city of about 8,000 people, lies to the northeast. Naval Air Station Fallon, one of the most important tactical air warfare training facilities in the United States Navy, is situated just east of town. The historic site of Fort Churchill, the remains of a 19th century military post, lies nearby as well. This is not uninhabited desert. This is a landscape with real infrastructure, real residents, and real buildings, some of them old and not built to modern seismic codes. At 6:29 in the evening on April 13, 2026, a magnitude 5.7 earthquake struck southeast of Lahontan Reservoir in the Dead Camel Mountains, a low volcanic range that rises above the desert floor between Silver Springs and Fallon. The main shock was located approximately 12.5 miles southeast of Silver Springs and 15 miles southwest of Fallon. Its depth was shallow, initially estimated at around 5 kilometers and later refined, which meant the energy arrived at the surface with relatively little attenuation from the intervening rock. The ground rolled for 20 to 30 seconds in many locations. Furniture moved, dishes fell. Residents from Douglas County to the south and Sparks to the northwest, across the mountains in the Truckee Meadows where Reno sits, reported feeling the shaking. Residents as far away as South Lake Tahoe on the California side of the Sierra Nevada submitted felt reports. By any measure, this was a genuinely significant earthquake. The Nevada Seismological Laboratory, working quickly in the hours following the main shock, catalogued at least 120 aftershocks by the morning of April 14th, 17 of which exceeded magnitude 3.0. Aftershock kits, portable seismic monitoring stations that can be rapidly deployed in the field to supplement the fixed instrument network, were dispatched to the epicentral area to provide finer-grained coverage of the continuing activity. These portable stations would allow the laboratory to track even very small events with greater precision, building a denser point cloud of earthquake locations that would ultimately reveal the fault geometry in 3 dimensions. Christy Rowe issued a public statement that combined the measured scientific communication her position required with a detail that stopped many readers in their tracks. There is no known fault at this location, the statement noted. The earthquake epicenter near the Dead Camel Mountains was situated 12 miles north of the epicenter of another significant earthquake, a magnitude 5.7 that had struck in December 2024 in the northern Mason Valley area. 2 major earthquakes in the same general region within 16 months, both occurring on structures that were not mapped in advance, began to suggest a pattern. Rowe confirmed what the data was showing. The Dead Camel Mountain sequence was unfolding on a fault nobody had documented before it announced itself. This earthquake sequence is on a fault we didn't know about before it started crossing the Dead Camel Mountains, Rowe said in public communications following the April 13th main shock. That statement, a direct parallel to what she had said about the Tonopah sequence just 6 weeks earlier, carried heavier weight this time because the stakes were higher. The towns of Silver Springs, Fallon, and Fernley are within feeling distance of the epicenters. Reports of minor damage began arriving in the days following the main shock, including cracked walls in some of the older buildings in Fallon and damage to some of the historic structures at the Fort Churchill site. Nothing catastrophic, nothing approaching the scale of damage a truly large earthquake would produce, but real, tangible evidence that this was not an event happening safely out in an empty desert. In the 10 days between April 13th and April 22nd, the Nevada Seismological Laboratory recorded a total of 371 earthquakes along the Dead Camel Mountains fault. 83 of those events had magnitudes of 2.5 or greater. The sequence was prolific, energetic, and persistent in a way that kept scientists and residents alike in a sustained state of watchful attention. The elevated risk of a larger earthquake following a significant main shock is a genuine seismological consideration, not a dramatization. After any earthquake above roughly magnitude 5.0, the probability of a larger event occurring in the near term on the same or adjacent fault segments is measurably elevated compared to background rates. This does not mean a larger earthquake will occur. It means the odds shift in a way that responsible scientists must communicate clearly. Rowe and the Nevada Seismological Laboratory did exactly that, stating publicly that the elevated risk existed while being careful not to frame it as a prediction or a certainty. The honest communication of probabilistic risk is one of the most difficult tasks in public seismology, and it is one that NSL handled with appropriate care. By April 22nd, a 4.8 magnitude earthquake struck, located approximately 13 miles southwest of Fallon and 20 miles north of Yerington, at a depth of about 4.6 miles. This quake was felt clearly in Carson City and in the communities of Genoa and Johnson Lane in Douglas County to the south. The aftershock sequence was not fading in the way scientists might hope. It was continuing to generate moderate-sized events weeks after the initial main shock, and each new significant earthquake brought another round of felt reports, another round of questions from residents about what was happening beneath them. The sequence near the Dead Camel Mountains was, by this point, beginning to attract the kind of sustained public and media attention that goes beyond the initial burst of news coverage a single earthquake generates. People in western Nevada were living inside an ongoing seismic sequence, feeling the ground move in the night, submitting reports, checking the Nevada Seismological Laboratory website for updates, and asking a question that is entirely understandable even if science cannot answer it with certainty. How much bigger can this get? And then, on the first day of May 2026, the answer to that question shifted again. At approximately 1:15 in the morning Pacific time, a magnitude 4.3 earthquake struck roughly 12 miles southeast of Silver Springs. 2 minutes later, a magnitude 5.2 earthquake struck in nearly the same location. Both events generated additional smaller aftershocks in the following minutes. The sequence, already 3 consecutive weeks of major seismic activity in western Nevada, had produced its third significant cluster at the same location, on the same previously unmapped fault crossing the Dead Camel Mountains. The magnitude 5.2 on May 1st was felt across an even wider area than previous events in the sequence. Shaking reports poured in from residents in Reno, Carson City, and the Lake Tahoe Basin on both the Nevada and California sides of the Sierra Nevada. Some reports came from as far as the Sacramento Valley in California, more than 150 miles from the epicenter, where the earthquake arrived as a gentle, rolling sensation that woke some people in the early hours of the morning. By daylight, more than 1,600 people had filed felt reports with the USGS, and the Nevada Seismological Laboratory was continuing to log aftershocks. What is happening beneath the Dead Camel Mountains and the surrounding terrain of western Nevada is, at its scientific core, a story about a fault that nobody knew existed until it started talking. It is also a story about what it means to live on a planet whose inner workings remain, in important ways, beyond the full reach of our instruments and our maps. The Nevada desert looks still and ancient from the surface, a landscape of weathered basalt and salt flats and distant purple mountains that seems to have been sitting quietly for an eternity. But underneath that stillness, the earth is working. It has always been working, and sometimes, without warning, it tells you something you did not know it was holding. There are 2 threads running through this story that deserve to be examined carefully, because they have implications well beyond the borders of Nevada. The first is the geological thread, the question of what precisely is happening in the rock beneath the Dead Camel Mountains, and why a fault of this character was invisible to every survey conducted before it moved. The second is the preparedness thread, the question of what the discovery of an unknown, active fault in a populated region means for the people who live there and the systems designed to protect them. On the geological side, the Dead Camel Mountains sit within the Walkerlane seismic belt, that long corridor of active faulting that runs northwest-southeast along the Nevada-California border region. Research published in the Journal of Geophysical Research in 2024, using high-precision GPS networks to model strain rates across the Walkerlane and Western Great Basin, found that the region contains zones of concentrated deformation that are not fully captured by the existing fault inventory. The Walkerlane is not a single, clean fault like the San Andreas, but rather a distributed system of structures interacting in complex ways, with strain accommodated partly on well-characterized faults and partly on structures that have not yet been mapped with full confidence. The Dead Camel Mountains themselves are a volcanic range, composed primarily of late Cenozoic basalts and other volcanic materials erupted during the extensional phases of basin and range tectonics. Volcanic rocks can be structurally complex, often fractured and altered in ways that make reading fault geometry from surface observation particularly challenging. The lavas can drape over and obscure older structural features, burying fault scarps under meters of volcanic material. This is one of several reasons why faults in volcanic terrain are systematically harder to map than faults in more coherent, sedimentary or crystalline rock. The fault crossing the Dead Camel Mountains, as it has revealed itself through the pattern of the earthquake sequence, appears to cut across the range in an orientation that was not predicted by the regional structural models. Rowe's description of it as crossing the range rather than running along it suggests a fault geometry that is oblique or transverse to the dominant northwest-southeast structural trend of the Walkerlane. If that interpretation holds up as the full dataset is analysed, it would indicate a fault that formed in response to local stress conditions, rather than being a simple product of the regional extension, potentially making it harder to anticipate from regional scale hazard assessments. For comparison, consider the 2020 Monte Cristo Range earthquake in Nevada, which research published in peer-reviewed journals afterward described as having complex fault geometry involving multiple fault segments that were not fully characterized before the event. The study found that the main shock activated both a primary fault segment and secondary structures, producing a pattern of surface deformation that required the full aftershock sequence to map adequately. This is a recurring theme in Nevada seismology. The region's seismic hazard is distributed across many faults, some well known and some entirely hidden, and the full geometry of individual fault systems often only becomes clear in the wake of significant earthquakes. Human history in the Dead Camel Mountains area adds another dimension to this story. The Lahontan Reservoir, which sits just north of the earthquake epicenters, was created by the Darby Dam on the Truckee River in 1905 as part of the Newlands Irrigation Project, one of the first federal water reclamation efforts in the American West. The reservoir has been an anchor of agriculture and community in the Churchill Valley for more than a century. Fort Churchill, situated downstream and to the south, was established in 1860 during the Pony Express era and the conflicts of the Great Basin frontier period. These are not transient settlements. They are places with deep roots in the regional landscape, and the ground beneath them is now shaking on a fault whose existence was not part of anyone's planning calculations. The question of planning, of seismic hazard assessment, and the gaps in our knowledge of active faults leads directly to a critical discussion that Christy Rowe has been advancing with considerable urgency. As she has done repeatedly since taking the directorship of the Nevada Seismological Laboratory, Rowe used the Dead Camel Mountain sequence to advocate for bringing the Shake Alert early warning system to Nevada. Shake Alert is an earthquake early warning program developed by the USGS in collaboration with several universities and state agencies, and it is already active in California, Oregon, and Washington. The system uses a dense network of seismic sensors to detect the initial faster-moving seismic waves of an earthquake and send alerts to mobile phones and public systems in the seconds before the slower, more destructive shaking waves arrive. Those seconds matter enormously. The alert from Shake Alert arrives faster than the damaging shaking because of the difference in travel speed between the initial P waves that the system detects and the S waves and surface waves that carry most of the destructive energy. Even a warning of 3 to 10 seconds can give people enough time to drop, cover, and hold on, to move away from windows and unstable objects, to pull a car to the side of a road, to halt a surgical procedure or a chemical process in a facility where abrupt interruption could amplify harm. At larger distances from the epicenter, the warning time grows to 15 or 20 seconds or more, enough time for meaningful protective action. Rowe calculated directly what shake alert would have meant for the Dead Camel Mountain sequence. If we had shake alert in Nevada, with an ideal installation, Reno would have had 10 to 15 seconds warning before feeling shaking from the 5.7 magnitude earthquake, she said. For a city of 250,000 people, 10 to 15 seconds of warning before ground shaking begins is not a trivial benefit. It is the difference, in the most vulnerable situations, between someone taking protective action and someone being caught completely unaware. Nevada does not yet have shake alert, but the situation is changing. The federal budget for fiscal year 2026 includes a directive for the USGS to develop a plan for adding Nevada to the shake alert program, which Rowe credited to strong support from Nevada's congressional delegation, including Congressman Mark Amodei. The translation of that planning directive into actual instrumented coverage across the state will take time, funding, and sustained political commitment, but the direction is set. The Dead Camel Mountains earthquake sequence arrived at a moment when the case for expanding earthquake early warning to Nevada was already being made, and the sequence made that case with a kind of concrete, felt urgency that abstract seismic hazard models rarely achieve. There is a broader lesson in this about the relationship between seismic knowledge and seismic preparedness. Scientists do not know where every active fault is. They never will, at least not with the monitoring capabilities and surface survey techniques currently available. What they do know is that any region of active tectonics, any place where the crust is being stretched or sheared or compressed by the forces of plate interaction, contains faults whose last surface expression has been erased by erosion, and whose presence will not be detected until the next earthquake. Nevada is such a region. So is California. So is the Pacific Northwest. So are many places across the globe where the record of geological activity stretches back far beyond the period of human observation. The appropriate response to this reality is not despair, but rather a recalibration of how we think about seismic risk. Risk is not simply a function of proximity to known faults. It is a function of being in a tectonically active region, where the possibility of an unknown fault exists alongside the mapped and catalogued ones. Building codes, emergency planning, public awareness, and early warning systems all need to be designed with this broader understanding of risk in mind, not just the risk posed by the faults we can see on the map. As late April turned into early May 2026, Nevada's earthquake sequence continued to evolve in ways that kept the scientific community carefully attentive. The fault beneath the Dead Camel Mountains was still generating events. The state as a whole was averaging a rate of seismic activity that was measurably above its long-term baseline, with the walkerlane and the central Nevada seismic belt both showing elevated activity compared to the preceding 5-year period. Whether this elevated activity represented a meaningful change in the state of stress across the regional fault system, or was simply within the range of natural variation in a region where earthquakes are endemic, was a question seismologists were working to answer with real-time data. The USGS Earthquake Hazards Program, with its comprehensive earthquake catalogue constantly updated from thousands of monitoring stations across the western United States, was providing the raw data stream for this analysis. At the Nevada Seismological Laboratory, scientists were cross-correlating the Dead Camel Mountain sequence with the earlier Tonopah swarm, looking for any evidence of stress transfer between the two zones. Stress transfer, the process by which a significant earthquake on one fault segment changes the stress state of adjacent regions, and thereby increases or decreases the probability of rupture on nearby faults, is one of the active frontiers of earthquake science. Understanding whether the Tonopah and Dead Camel Mountain sequences were related, or were independent manifestations of the broader tectonic background, was a question with practical implications for hazard assessment across the region. What makes the Nevada situation in the spring of 2026 particularly instructive for anyone interested in how the Earth works is that it strips away the comfortable abstraction that so often surrounds discussions of geological hazard. Fault maps and seismic hazard models are powerful tools. They are built on decades of painstaking research by hundreds of scientists, and they represent humanity's best current understanding of where and how the Earth moves. But they are not complete. They cannot be complete, because the Earth does not reveal all of its architecture at once. Some of it waits, patient and deep and invisible, until the accumulated stress of centuries or millennia finally overcomes the strength of the rock, and the fault slips, and the ground shakes, and the instruments record it, and the scientists say, with the honest matter-of-factness that good science demands, that they did not know this fault was there. That moment of discovery, arriving through the seismograph rather than through any planned survey or deliberate investigation, is both a scientific opportunity and a reminder of the limits of what we know. The Dead Camel Mountains fault introduced itself through its own rupture. The fault beneath the southern Monitor and Antelope Ranges made its existence known through weeks of trembling. Both of these structures were there all along, carrying stress in silence, waiting for the moment when the balance tipped. And in that moment of tipping, they told the world something new. The science of finding hidden faults before they rupture, rather than after, is one of the most pressing and genuinely difficult challenges in modern geophysics. It is a challenge being pursued through several complementary approaches, none of them individually sufficient, all of them advancing in ways that give scientists genuine reasons for measured optimism, even as the fundamental difficulty of the problem remains stubbornly unresolved. The spring of 2026 in Nevada has given that challenge a new urgency, a fresh set of case studies, and a more concrete set of faces to put on what might otherwise seem like an abstract scientific problem. One of the most powerful tools in the effort to find hidden faults is LIDAR, which stands for Light Detection and Ranging. LIDAR uses rapid pulses of laser light emitted from aircraft to measure the precise elevation of the ground surface at extremely high resolution, generating dense point cloud datasets that can be processed to reveal subtle topographic features that are entirely invisible to the human eye, to standard aerial photography, and to conventional satellite imaging. The critical advantage of airborne LiDAR for fault mapping lies in its ability to effectively see through vegetation. In forested terrain, a standard aerial photograph shows the tops of trees and nothing else. LiDAR can mathematically subtract the vegetation return and display only the bare earth beneath it, exposing fault scarps, linear valleys, and offset stream channels that would otherwise remain completely hidden under a canopy of brush and trees. In the arid desert terrain of Nevada, where vegetation is sparse compared to wetter climates, the advantage of LiDAR works somewhat differently, but it can still reveal low-relief fault features that have been smoothed and subdued by erosion to the point where they are effectively imperceptible from ground level, yet retain just enough topographic signature to appear as a faint but detectable anomaly in high-resolution elevation data. A fault scarp that formed several thousand years ago in Nevada's desert environment might stand only a meter or two high after millennia of erosion, rounding, and partial burial by alluvial sediment. From the ground, standing next to it, a person might simply perceive a slight rise in the terrain and think nothing of it. From a satellite photograph, the illumination angle and the scale of the image make the feature invisible. But in a LiDAR-derived digital elevation model rendered with precise hillshade illumination from a low angle, that same meter-high scarp can emerge as a crisp, unambiguous linear feature cutting across the landscape, its geometry revealing the fault trace as clearly as if someone had drawn it on a map. This technique has transformed fault mapping in many regions, revealing previously unknown fault scarps in the Pacific Northwest, in the Basin and Range, and in the Wasatch Front region of Utah where fault scarps run close to major population centers. The problem is coverage, and it is not a small problem. LiDAR surveys are expensive and logistically demanding to acquire. The entire state of Nevada has not been covered at the resolution necessary to systematically map subtle fault scarps across every mountain range and valley floor in the state. Prioritization decisions are made based on population density, known hazard levels, existing funding streams, and the advocacy of local scientists and emergency managers. The areas around Tonopah and the central Nevada interior, because of their sparse population and their location in a region historically assessed as moderate rather than extreme on the seismic hazard scale, have not been priorities for the most intensive LiDAR coverage programs. The same broad gap in coverage is true of many parts of the Basin and Range. The regions where hidden faults are most likely to exist in significant numbers are precisely the regions where the investment in high-resolution topographic survey has been least comprehensive. There is a painful irony in this. The places that most need the most thorough fault mapping are often the places least likely to receive it, because the known hazard in those areas is lower and the population is smaller, which means the political and funding pressure to prioritize them is weaker. Satellite-based geodesy, using instruments like the European Space Agency's Sentinel-1 constellation of radar satellites and NASA's Jet Propulsion Laboratory interferometric programs, provides another important line of evidence for studying faults both before and after they rupture. Interferometric synthetic aperture radar, universally known in the seismological community as INSAR, can detect millimetre-scale changes in the distance between the satellite and the ground surface across wide geographic areas, changes produced by the deformation that accompanies fault slip. When a fault slips during an earthquake, the ground surface above and around it deforms in characteristic patterns that depend on the fault's geometry, its depth, and its orientation. These deformation patterns create distinctive signatures in INSAR data, recognizable to trained analysts, that allow scientists to infer the location, geometry, and amount of slip on the fault at depth, even when no surface rupture is visible from the ground. INSAR was applied to the 2008 Reno Mogul earthquake swarm and proved scientifically revealing. Published research in Geophysical Research Letters documented that analysis and modelling of INSAR data from the Mogul sequence indicated the main event was produced by slip on a previously unrecognised strike-slip fault in the Reno Basin, confirming and extending what the seismograph network had already suggested. The surface deformation measured by the satellite covered an area of more than 150 square kilometres, a much larger footprint than anyone might have expected from a magnitude 4.9 earthquake, and the pattern of that deformation was consistent with the westward migration of walkerlane-style dextral faulting into the Reno Basin, a finding with implications for the long-term seismic hazard of the region that extend well beyond the immediate swarm. For the Dead Camel Mountain sequence of 2026, INSAR data from satellites passing over western Nevada during the weeks of main shock and aftershock activity was being actively processed and incorporated into the scientific analysis. The deformation signal from a magnitude 5.7 earthquake is detectable, but confined to a relatively modest geographic footprint compared to larger events. In the arid terrain of the Nevada desert, where the vegetation signal does not complicate the radar return in the way it does in agricultural or forested areas, the INSAR data contributed meaningfully to constraining the fault model and refining the understanding of where exactly the rupture occurred and in what orientation. The combination of precise earthquake hypocenter locations from the dense aftershock kit monitoring network, together with the surface deformation field from radar satellite imagery, gives scientists a significantly richer and more three-dimensionally resolved picture of a fault's geometry than either dataset could provide in isolation. Field reconnaissance, the old-fashioned and still irreplaceable work of geologists and seismologists walking the ground with eyes and instruments, also played a role in the response to the Dead Camel Mountain sequence. After significant earthquakes in Nevada, teams from the Nevada Seismological Laboratory, the Nevada Bureau of Mines and Geology, and the USGS have a consistent practice of deploying rapidly to the epicentral area to look for surface rupture, ground cracking, liquefaction of saturated sediment, and other primary or secondary effects of the ground shaking. The Dead Camel Mountains area received this attention following the April 13, 2026 main shock, with researchers searching the volcanic and alluvial terrain for any fresh expression of fault movement at the surface. In some Nevada earthquakes, the rupture reaches the surface clearly and dramatically. In others, the slip is contained entirely at depth, and the surface shows no direct expression of the fault movement, even when the earthquake is large enough to be felt hundreds of miles away. Whether the Dead Camel Mountains fault produced any direct surface rupture was one of the questions the field teams went out to answer. The broader context for all of this scientific response, the rapid instrument deployment, the INSAR analysis, the field surveys, the hypocenter relocation studies, is the ongoing national effort to maintain and improve the seismic hazard knowledge base that underlies building codes, land use planning decisions, insurance frameworks, and emergency management protocols across the United States. The USGS publishes the National Seismic Hazard Model, a comprehensive probabilistic assessment that specifies the expected ground shaking at any location in the country over various time windows. This model is updated periodically, most recently in 2023, as new data on fault locations, slip rates, rupture histories, and ground motion characteristics accumulates. The discovery of a previously unknown active fault in a region changes the inputs to that model, and, if the fault is close enough to populated areas or capable of producing large enough earthquakes, may warrant revisions to the local hazard assessment. The fault beneath the Dead Camel Mountains, discovered in April 2026 through the earthquake sequence itself, will take months to years of careful analysis before its characteristics are understood well enough to be formally incorporated into the National Hazard Model. Its slip rate, which determines how frequently it ruptures and how large those ruptures can be, is currently entirely unknown. Its full length, which constrains the maximum magnitude earthquake it can produce, is still being defined from the aftershock distribution and the field surveys. Its history of past ruptures, which would allow paleoseismologists to calculate a recurrence interval, has not yet been investigated through trenching studies. All of these are unknowns that will need to be resolved through patient and systematic scientific work before the fault's full contribution to seismic hazard in the Churchill Valley and surrounding region can be properly quantified. In the meantime, the buildings, roads, pipelines and communities in the area are being assessed against a seismic hazard model that does not yet include this structure. This is not negligence, and it is not bureaucratic failure. It is the inevitable and honest consequence of the gap between the pace at which the Earth reveals its architecture and the pace at which science can characterize, validate, and communicate what it has learned. That gap exists everywhere in the world where tectonic activity produces hidden faults, and it has real consequences distributed across probabilities rather than certainties. The honest acknowledgement of this gap, and the sustained investment required to narrow it, is one of the most important things that geological science can offer to the broader project of building safer communities. Nevada's situation in this regard is not unique, but it illustrates the problem with unusual clarity and urgency. The Pacific Northwest faces a version of the same dynamic at a larger scale, where the Cascadia subduction zone represents a known but incompletely characterized source of potential megathrust earthquakes of magnitude 8 or 9, and where individual crustal faults scattered across Oregon and Washington are poorly mapped and insufficiently studied relative to the hazard they represent. The New Madrid seismic zone in the central United States, responsible for some of the largest earthquakes in the written historical record of North America in 1811 and 1812, remains difficult to fully characterize because its causative faults are buried under many meters of soft sedimentary material deposited by the Mississippi River system, and their surface expression is ambiguous and hard to interpret with confidence. In each of these regions, the same fundamental geological truth applies with equal force. The inventory of mapped active faults is not the complete set of active faults. Some portion of the seismic hazard in any tectonically active region is hidden, waiting. Now, before we continue deeper into the science of the Dead Camel Mountain sequence, this is a good moment to say something that we always try to make clear on this channel. Everything we are discussing here is grounded in verified scientific sources, in statements from the Nevada Seismological Laboratory, in data published by the USGS, in peer-reviewed research on basin and range tectonics and walkerlane seismology. But science is not a finished product. It is a process, and the process of understanding the 2026 Nevada sequences is still very much underway. We encourage you, as always, to go directly to the primary sources, to read the researchers' own words, to look at the seismic data on the USGS Earthquake Hazards website and the Nevada Seismological Laboratories public monitoring pages, and to form your own informed views rather than accepting any single interpretation, including ours, as the complete picture. The human dimension of the Dead Camel Mountain sequence deserves careful attention, because this is not a story happening only in the domain of scientific instruments and academic papers. It is happening in the lives of real people in specific communities, and the texture of their experience provides important context for understanding what the discovery of an unknown active fault actually means at the level of daily life. The town of Fallon, Nevada, sits about 15 miles from the epicentral area of the Dead Camel Mountain sequence. Fallon has a population of roughly 8,000 people, making it the largest community in Churchill County. It is an agricultural hub in a desert region made farmable by the Newlands Irrigation Project, one of the first federal water reclamation efforts in the American West, which in 1905 completed the Darby Dam on the Truckee River and created Lahontan Reservoir just to the northwest of town. Fallon is also the home of Naval Air Station Fallon, one of the most important tactical aviation training facilities in the United States Navy, where naval aviators have been honing combat flying skills for generations. The community has deep roots, a strong sense of local identity, and buildings that span more than a century of construction, from adobe and unreinforced masonry structures built in the early 20th century without any consideration of seismic loading, to modern construction built under building codes that were calibrated to the seismic hazard understood before the Dead Camel Mountains fault made its existence known. When the magnitude 5.7 earthquake struck on the evening of April 13, 2026, residents of Fallon felt the ground move beneath them with the distinctive rolling, lurching quality that distinguishes a significant earthquake from the smaller tremors that might have become somewhat familiar in the weeks leading up to it. The shaking lasted 20 to 30 seconds in many locations, which is long enough for alarm to fully register, for objects to fall from shelves, for the cracking and groaning of building structures to become audible and concerning. In the hours and days following the main shock, reports of minor damage began to surface. Cracks appeared in walls of older buildings. Some chimneys and unreinforced masonry features showed damage consistent with the forces of moderate ground shaking. The historic structures at Fort Churchill State Historic Park, roughly 20 miles to the south of Fallon, sustained damage to some of the preserved adobe ruins that form the physical heart of one of Nevada's most significant 19th century historical sites. Fort Churchill was established in 1860 during a period of intense conflict between settlers and the Paiute people of the Great Basin, and it served as a critical military post during the early years of Nevada's territorial period. The fort's adobe buildings were constructed from sun-dried brick, the same material used across the arid American West for centuries because of its availability and thermal properties. Adobe is, however, one of the most seismically vulnerable building materials in existence. Its mass and rigidity make it prone to brittle failure during earthquake shaking, and its age at Fort Churchill, now more than 160 years, means it has experienced decades of additional weakening through weathering and cumulative minor damage from previous seismic events. The damage to Fort Churchill from the April 2026 sequence, described in official communications as minor, is a sobering reminder that the irreplaceable physical heritage of the American West, the structures that connect living communities to their histories, is stored in materials that were built in complete ignorance of the seismic forces that share their landscape. Silver Springs, the community closest to the epicenters of the sequence, is a small unincorporated community in Lyon County, with a few thousand residents, situated in the broad valley between the Pine Nut Mountains and the Dead Camel Mountains. Its residents experienced the Dead Camel Mountain sequence more intensely than anyone else in the region, feeling not just the magnitude 5.7 main shock, but the long parade of aftershocks that followed it across the weeks of continued activity. The experience of living inside an extended earthquake sequence, of never quite being sure when the next jolt will arrive, of sleeping lightly and waking to each new tremor with a moment of uncertainty about how large it will grow, is a form of sustained low-level stress that the simple count of earthquake magnitudes does not fully capture. It affects how people feel in their homes, how confidently they sleep, how much mental energy they invest in monitoring the seismic situation, rather than attending to the ordinary business of their lives. The USGS Did You Feel It system, which allows members of the public to submit reports of their experience during each earthquake, providing details about the intensity of shaking they experienced and any effects they observed, received thousands of submissions during the Dead Camel Mountain sequence. These crowdsourced reports serve a genuine scientific function. They fill in the spatial gaps between monitoring stations, providing ground truth data on how shaking intensity varied across the region in ways that the instrument network alone cannot fully resolve. They also serve a civic function, giving people a constructive outlet for their experience and a direct contribution to the scientific understanding of the events they have lived through. Rowe and her colleagues explicitly encouraged residents to submit reports, noting that even accounts of very light shaking from distant locations contribute useful information to the seismological analysis of the sequence. The Nevada Seismological Laboratories' response to the Dead Camel Mountains main shock demonstrated the kind of rapid, professional mobilization that serious seismic monitoring requires. Within hours of the magnitude 5.7 earthquake on April 13th, the laboratory was already deploying aftershock kits, portable seismic monitoring stations that can be rapidly installed in the field to supplement the fixed instrument network around an epicentral area. These portable stations were designed for exactly this kind of situation, where a significant earthquake has occurred in a region where the permanent network is not dense enough to precisely locate and characterize the potentially hundreds of aftershocks that will follow in the coming days and weeks. By April 22nd, the laboratory had recorded 371 earthquakes along the Dead Camel Mountains fault, 83 of them with magnitudes of 2.5 or greater. The aftershock kits were providing higher fidelity recordings of the continuing activity, giving the scientists more precise hypocenter locations and better constrained focal mechanisms that would ultimately feed into a three-dimensional model of the fault's geometry. The public statement that Christy Rowe issued about the sequence contained words that stopped many readers and listeners in their tracks, not because they were alarming in tone, but because of what they revealed about the limits of geological knowledge. This earthquake sequence is on a fault we didn't know about before it started, crossing the Dead Camel Mountains, she said. We've had reports of minor damage in Fallon and at Fort Churchill to some of the historic buildings. And then, explaining why the fault had been unknown, she offered the sentence that captures the essential challenge of seismic hazard in tectonically active regions with particular clarity. When a fault lies quiet for thousands of years, erosion can erase it from the landscape. It lies hidden until the next earthquake. That sentence describes a process that geologists understand well, and that has profound practical implications for how we think about the completeness of our knowledge of seismic hazard. A fault that last ruptured 10,000 years ago in the Nevada desert would have produced a scarp, a visible step in the terrain where one side of the fault dropped relative to the other. In the decade immediately following that ancient rupture, the scarp might have been several meters high and clearly visible across the landscape. But over the following centuries, alluvial fans shed from the surrounding mountain ranges would have gradually buried the lower portions of the scarp. Desert varnish and biological soil crusts would have colonized its surface. Windblown dust and sand would have accumulated against its base and softened its profile. Occasional flash floods would have deposited sediment sheets across the valley floor, burying whatever remained of the original topographic expression. After 10,000 years of this patient geological housekeeping, the scarp might be entirely invisible at the surface, leaving behind nothing that a field geologist walking the terrain would confidently identify as a fault feature, rather than simply a natural variation in the topography. The only reliable way to detect such a feature from the surface at this point would be through the application of sophisticated technology, high-resolution LiDAR scanning followed by careful analytical processing, or through the kind of systematic regional paleoseismic survey that requires substantial funding, extensive fieldwork, and years of dedicated effort. Neither of these has been applied comprehensively to the area of the Dead Camel Mountains. And so the fault lay there, undetected, accumulating the stress that would eventually produce the April 13, 2026 main shock, with no warning to the science, no warning to the communities, no warning to anyone. The Dead Camel Mountains themselves are a geologically interesting feature in their own right, quite apart from the seismic sequence that has now brought them to wider attention. They are a low volcanic range composed primarily of late Cenozoic basalts and other volcanic materials, erupted during the extensional phases of basin and range tectonics, when the thinning crust allowed mantle-derived melts to reach the surface. The range sits within the broader walkerlane seismic belt, and its volcanic character creates specific challenges for fault mapping that go beyond the general difficulties already described. Volcanic rocks can be structurally complex, often intensely fractured and chemically altered by hydrothermal fluids moving through the hot volcanic pile during and after eruption. These rocks commonly display multiple generations of fracturing overprinted on each other, making it difficult to identify which fractures are tectonic faults, capable of seismic rupture, and which are simply cooling joints or hydrothermal alteration features with no seismic significance. The lavas can also drape over and partially bury older structural features, covering fault scarps under meters of volcanic material that gives no surface indication of what lies beneath. The fault crossing the Dead Camel Mountains, as it has revealed itself through the detailed pattern of the earthquake sequence, appears from the available data to cut across the range in an orientation that was not well predicted by the regional structural models derived from mapping the known faults of the walkerlane. Rowe's description of it as crossing the range suggests a fault geometry that is at least partially transverse to the dominant northwest-southeast structural trend that characterizes most of the walkerlane belt. If that interpretation holds up as the full three-dimensional dataset from the aftershock sequence, and the INSAR analysis is integrated, it would indicate a fault whose local geometry reflects specific stress conditions in the Dead Camel Mountains area that deviate from the simple regional pattern. Such locally anomalous structures are systematically harder to anticipate from regional scale hazard assessments, precisely because the methods used to extrapolate hazard across large areas tend to smooth out local variations in structural orientation and fault character. The question of what triggers any specific earthquake sequence, why this fault moved now rather than 50 years ago or 50 years from now, is one that seismology cannot yet answer with precision for individual events. The broad answer is straightforward. The fault moved because the accumulated stress on the fault plane exceeded its frictional resistance at some point, and that failure propagated as a rupture of whatever dimension the stored elastic energy could sustain. But the specific trigger, the last increment of stress that pushed the system from lock to slipping, is often unclear. In some cases, the trigger is identifiable. A large earthquake on a nearby fault can transfer stress to adjacent structures in ways that are detectable through careful analysis, and documented cases of earthquake triggering by static stress transfer are well established in the scientific literature. In other cases, the trigger appears to be internal to the fault zone itself, perhaps related to slow creep, to variations in pore fluid pressure, or to the accumulation of microscopic damage over time that gradually weakens the fault before final failure. For the Dead Camel Mountain sequence, the question of whether there was a specific external trigger is being examined as part of the ongoing scientific analysis. The Yerington area earthquake of December 2024, a magnitude 5.7 event that struck on an unmapped fault in the northern Mason Valley, roughly 12 miles to the south of the Dead Camel Mountains epicenters, is a natural candidate for investigation. Two significant earthquakes separated by about 16 months, both on previously unmapped faults, both in the same general region of western Nevada, invite the question of whether there is a physical connection between them. The stress changes produced by the December 2024 Yerington earthquake would have altered the stress field in the surrounding region, potentially bringing nearby fault segments closer to failure in some orientations, and pushing them further from failure in others. Whether the Dead Camel Mountains fault was in a position to be triggered by those stress changes is a calculation that requires detailed knowledge of both fault geometries and orientations that was not available before the 2026 sequence provided it. The December 2024 Yerington earthquake had its own story of geological discovery embedded in it. Field reconnaissance and INSAR analysis following that event revealed that the earthquake occurred on an east-northeast striking fault and triggered surface fracturing along an orthogonal, northwest striking secondary fault, a pattern of orthogonal rupture that had not been anticipated from the existing fault maps of the area. The lesson was the same one that Nevada keeps delivering through its seismic record, that the fault inventory is incomplete, that the known structures do not represent the complete set of active features, and that the gaps in the map are not evidence of the absence of hazard, but simply evidence of the limits of what has been observed and documented so far. The accumulation of these cases across the recent seismic history of Nevada, the Mogul Fault discovery in 2008, the complex Monte Cristo Range geometry revealed in 2020, the Yerington orthogonal rupture of 2024, the Tonopah Swarm Fault of early 2026, and now the Dead Camel Mountains Fault of April 2026, builds an increasingly compelling picture of just how substantially the known fault inventory underrepresents the true population of active seismic structures in this region. Each new discovery is not an isolated surprise, but rather another data point in a pattern that is becoming harder to ignore. The pattern says that the basin and range and the walkerlane contain many more active faults than the maps show, that those faults can generate significant earthquakes when they move, and that the communities living in the region face a level of seismic risk that is not fully captured by hazard assessments built on the documented fault inventory alone. This is the broader scientific and societal context within which Christy Rowe's advocacy for the Shake Alert early warning system needs to be understood. Her advocacy is not simply a reflexive argument for more technology. It is grounded in a specific analysis of the situation Nevada faces, a state with confirmed high seismic activity, an incompletely mapped fault inventory, a growing body of evidence that unknown active faults exist throughout the region, and no earthquake early warning system to provide even a few seconds of alert before damaging ground shaking arrives at populated areas. Shake Alert was developed over more than a decade of collaborative work between the USGS, several university seismology programs, and state agencies along the Pacific coast. The system went operational in California in 2019, providing public alerts through the smartphone-based MyShake app and other distribution channels. Oregon and Washington followed in 2021. The system's operational performance during California earthquakes since its activation has been instructive. For the 2019 Ridgecrest earthquake sequence in Southern California, for example, Shake Alert generated alerts that reached parts of the Los Angeles metropolitan area several seconds before the strongest shaking arrived. For the 2020 Monte Cristo Range earthquake in Nevada, just across the border from the Shake Alert coverage area, no warning was available because Nevada was not yet part of the network. The physics of why early warning is possible, and what its practical limits are, deserves clear explanation because it bears directly on the question of what Shake Alert could realistically offer to western Nevada. When a fault ruptures, it generates several types of seismic waves that travel outward through the crust at different speeds. The first to arrive at any distant location are the P waves, compressional waves that travel through rock at roughly 6 km per second in typical crustal material. P waves carry relatively little energy and cause relatively little damage at the surface. They are followed by S waves, shear waves that travel at roughly 3.5 km per second and carry significantly more energy. After the S waves come the surface waves, which travel more slowly still, but often carry the most destructive energy of all, particularly for large earthquakes. The difference in travel speed between P waves and S waves creates a window of time at any given location, a window that grows with distance from the epicenter, during which the P wave has already arrived and been detected by the monitoring network, but the more damaging S waves and surface waves have not yet reached the location being warned. Shake Alert exploits this window. When seismic stations nearest to a rupture detect the characteristic arrival of P waves, and the system's algorithms determine that a significant earthquake is occurring, an alert is transmitted electronically to smartphones, emergency systems, automated industrial controls, and other receivers at a speed limited only by the speed of light in fiber and wireless networks, which is many times faster than the speed of seismic waves in rock. The alert arrives at distant locations before the damaging shaking does, providing a warning window whose duration increases with distance from the epicenter. For the magnitude 5.7 Dead Camel Mountains earthquake of April 13, 2026, Rowe calculated that a fully operational Shake Alert system in Nevada would have provided approximately 10 to 15 seconds of warning to the city of Reno before the damaging shaking arrived there. 30 miles separates the epicenter from downtown Reno. The time required for the S-waves to travel that distance, minus the few seconds needed for the system to detect the earthquake and transmit the alert, yields that 10 to 15 second window. In absolute terms, 10 seconds is not a long time, but in the context of earthquake preparedness, it is enough time for a person to take protective action, to drop to the floor, cover their head, and brace against a stable structure rather than being caught standing or moving. It is enough time for a surgeon to pause a delicate procedure, enough time for a driver to pull over and stop, enough time for schools to initiate practiced protective drills that can reduce injuries from falling objects, enough time for automated systems to shut down sensitive industrial processes, halt trains on elevated tracks, or open fire station doors so emergency vehicles can respond without being blocked by a warped structure. The federal budget for the fiscal year 2026 includes a directive for the USGS to develop a plan for adding Nevada to the Shake Alert program, a provision that Rowe credited in part to strong advocacy from Nevada's congressional delegation, including Congressman Mark Amodei. This is a planning directive, not an implementation one, and the path from a planning directive to an operational warning network covering a state as large and geographically varied as Nevada is long, and requires sustained funding and political commitment over multiple budget cycles. But the existence of the directive is meaningful. It represents a formal federal acknowledgement that Nevada's seismic situation warrants the same investment in early warning infrastructure that has already been made for its neighbors to the west. The urgency of that investment is now underscored by 3 consecutive weeks of major earthquake activity in western Nevada through April and into May 2026. The Dead Camel Mountain sequence has not stopped. Following the April 13th main shock, a 4.8 magnitude event struck on April 22nd, felt in Carson City and Douglas County. Then, in the early hours of May 1st, a 4.3 magnitude earthquake struck roughly 12 miles southeast of Silver Springs, followed within 2 minutes by a 5.2 magnitude event in nearly the same location. That May 1st sequence was felt across a wide region, with reports arriving from Reno, Carson City, the Lake Tahoe Basin on both sides of the Sierra Nevada, and from parts of the Sacramento Valley in California more than 150 miles to the west. More than 1,600 people filed felt reports with the USGS within hours of the May 1st sequence. The sequence is still ongoing. The Nevada Seismological Laboratory, working through this sustained period of activity, has now recorded hundreds of earthquakes along the Dead Camel Mountains fault. Each new event adds a data point to the growing three-dimensional picture of the fault's geometry. The aftershock kits deployed in the field are providing high-fidelity recordings of even the smallest events, giving the scientists hypocenter locations precise enough to begin tracing the fault plane's orientation, dip angle, and along strike length with confidence. The work of translating this raw seismic data into a coherent geological model of the previously unknown fault is proceeding in parallel with the ongoing monitoring of new events, a situation that requires managing the tension between the need for rapid communication to the public about what is happening and the need for careful analysis before drawing conclusions that could prove premature. This tension between the pace of public communication and the pace of scientific analysis is a recurring challenge in seismology and in science communication more broadly. When the ground is shaking beneath populated communities and people want to know what is happening and whether they are in danger, the demand for clear, timely information is entirely reasonable, and the pressure on scientists to provide it is intense. But the honest answer to many of the most important questions, how large could this get? Is the sequence winding down or escalating? How long will it continue? Is this fault connected to larger structures? Always involves probabilistic uncertainties that are difficult to communicate clearly to a public that understandably wants definitive answers. The Nevada Seismological Laboratory has handled this tension professionally and responsibly throughout the spring 2026 sequences, providing regular updates, stating clearly what is known and what remains uncertain, and resisting the temptation to offer false precision about outcomes that the science cannot yet constrain. What the science can say with confidence is that the Dead Camel Mountains fault has now been active for more than 3 weeks, that it has produced one earthquake of magnitude 5.7 and several in the mid-4 to low-5 range, that aftershocks are continuing and will likely continue for weeks to months at diminishing rates, and that the elevated probability of a larger event that exists following any significant main shock has not yet returned to background levels. The statement that there is an elevated risk of a larger earthquake following this one is honest and appropriate. It does not mean such an earthquake will occur. The overwhelming majority of earthquake sequences do not produce larger events than their main shock. But the possibility exists at a level above the background rate, and communicating that honestly to communities that are planning their daily lives around the ongoing activity is part of the responsible public function of a seismological laboratory. The broader question of what the discovery of multiple unknown active faults in Nevada within a short period of time means for how the state thinks about earthquake preparedness is one that deserves sustained attention from policymakers, planners, engineers, and the public alike. The inventory of known active faults in Nevada was always understood by geologists to be incomplete. The degree to which it is incomplete has now been illustrated with particular concreteness through the Tonopah sequence and the Dead Camel Mountain sequence, both unfolding within weeks of each other in early 2026. The lesson is not that Nevada is more dangerous than it was thought to be. The underlying tectonic reality has not changed. The lesson is that the maps we use to visualize and communicate that danger are less complete than their apparent precision might suggest, and that the gap between the map and the reality needs to be narrowed through investment in better survey technology, better monitoring infrastructure, better early warning systems, and better public education about what it means to live in a seismically active landscape. There is something in the experience of Nevada's spring 2026 earthquake sequences that goes beyond the specific scientific and policy questions, something that touches on a more fundamental relationship between human civilization and the planet it inhabits. We build our cities, our highways, our reservoirs, our military installations, our farms and ranches and communities on the surface of a planet that is geologically alive in ways that no amount of mapping will ever fully capture. The ground beneath us is not a passive stage for human activity. It is an active system shaped by forces operating at timescales that make all of recorded human history look like an eye blink, forces that are indifferent to our presence, our plans, our knowledge, or our preferences. The Nevada desert gives this reality an unusual visibility. The landscape itself is the product of fault movement. Every range front a fault face, every valley floor a dropped block, every hot spring and geothermal feature a symptom of the heat that rises through the thinned and fractured crust from the mantle below. The geological processes that created this landscape are still operating, still accumulating stress on hundreds of fault structures, still working toward the next rupture on whatever fault is closest to failure at any given moment. Some of those faults are well known and carefully monitored. Some are partially characterized, their existence documented but their full geometry and slip rate incompletely understood. And some, as the spring of 2026 has demonstrated once more, are entirely unknown, hidden beneath the surface expression of a landscape that has had thousands of years to erase whatever traces their last movement left behind. The people who study this system, the seismologists and geologists and geodesists who spend their careers trying to understand and communicate the risks it poses, are doing work that is consequential in the most literal sense. The knowledge they build, piece by piece through decades of field surveys and instrument deployments and data analysis, is what makes it possible to build safer buildings, to plan safer communities, to issue warnings that save lives. Christy Rowe, sitting in front of seismic monitoring screens at the Nevada Seismological Laboratory in Reno, watching the aftershock counts climb through the spring of 2026, is doing exactly that work. Her lab is mapping the architecture of the unknown, one earthquake at a time, building a more complete picture of what lies beneath the Nevada desert than anyone had before the desert chose to speak. The Dead Camel Mountains fault has now been introduced to science and to the world. It has a name, informal but geographically specific, and it has a growing body of seismic and geodetic data that will eventually allow it to be fully characterized. It will appear on maps that did not previously include it. It will be part of hazard assessments for the surrounding communities in ways it was not before April 13, 2026. It may, as the data mature, prompt a review of building standards and emergency planning in Churchill and Lyon counties. And it will take its place in the long list of Nevada faults that were discovered not through planned investigation, but through the unplanned rupture of the crust itself, the Earth's most direct and irreversible method of introducing its hidden structures to the science that studies them. The ground beneath Nevada is not finished talking. It has been saying something urgent for more than 3 weeks now, in the language of seismic waves and ground displacement, and the accumulated experience of thousands of people who have felt their homes shake in the night. The instruments are listening to every word. The scientists are working to translate what they hear into knowledge that protects lives. And the rest of us, wherever we live on this geologically active planet, would do well to pay attention to what Nevada is showing us about the limits of what we know and the importance of being prepared for what we do not yet know is coming. Thank you for spending this time with us here on Deep Space Intelligence. Stories like this one, about the living Earth beneath our feet, about the science that tries to understand it, and about what it means for the people who live on its surface, are exactly why this channel exists. As always, we encourage you to go to the primary sources, to look at the USGS data for yourself, to read the Nevada Seismological Laboratories public statements, to consult the peer-reviewed research on basin and range geology, and to form your own informed conclusions. The science here is alive and still developing, and the most valuable thing we can offer you is not a final answer, but an honest and careful guide to the questions that matter most. My name is Liam, and this is Deep Space Intelligence. We will see you in the next one.